All right, guys, welcome back for the last lesson of this week. So 4.3 is about conditional probability. So in this section, we're going to go back to the concept of independent and dependent events. So when we talked about dependent events, we said the probability of one event occurring was dependent to another event if it affected the probability of that other event. So we talked about like if it's raining, you're more likely to bring an umbrella. So the events rain and the event umbrella are dependent because one affects the other. So now we're going to talk more about how do we actually relate those probabilities when they're dependent. We talked about how to relate the probabilities when they're independent of each other, but we completely skipped the dependent side of things. So that's the part we're going to talk about today, dependent events. So when we're calculating the probability of the combination of dependent events, we're going to have to consider what we call a conditional probability. So a conditional probability is a probability that an event occurs given that another event has occurred. So we have some notation here. If I want to write the probability of A given B, and given's kind of a key word here, we would write that in symbol form to kind of save some room on our paper. We would write P of A given B. So this vertical line between A and B, we call that given. So this is the probability of event A occurring given that event B has occurred. So let's look at this here. Does each situation give a conditional probability? Explain your answer. So A, the probability that you are given a car for your birthday. Let's see, what events did we have here? One event is you're given a car. Is there any other event though? Is there a given condition? There is the word given, but are they giving you a condition? No, this is not conditional probability. The word given here has nothing to do with the condition that's being given to you. The word given has multiple meanings, right? And they're trying to throw you off here. I could change this to a conditional probability. I could say the probability that you get a car given that it is your birthday. Or I could say the probability that you get a car on your birthday given that you're turning 16. Or the probability that you get a car for your birthday given that you have been good in school or in general. So no, I would say no here. My explanation would be that the term given is not giving a condition in this context. Okay. We do, though, when we're looking for conditional probabilities, we do look for that word given. It's usually a dead giveaway that we're looking at a conditional probability, but we have to be aware that the word given does have multiple meanings. So let's look here. It says the probability that you win a second round of a game given that you won the first round. So again, here's that word given, but this time you are given a condition. The condition is that you won the first round. Does winning the first round affect the possibility of winning the second round? Maybe, maybe not. Either way, this is a conditional probability because there is a condition. The condition is that you win the first round. So we're looking for the probability of something different, something that you win a second round, given of the condition that you win the first round. All right, so let's look at some actual probabilities here. So we have a rule. It says a rule, probability of A given B. The conditional probability of A given B is the fraction of the outcomes in B that are also in A. So let's explain with this Venn diagram. It says this Venn diagram shows who went to a concert and who bought a song. A person is randomly chosen from this list. Let event A be the person attended the concert. Let event B be the student bought a song. What is the probability of A given B? Okay, when we're looking at a conditional probability like this, the first thing I'm going to look at is my condition. The second letter is the condition. That means instead of looking at all of the outcomes in the sample space, we're only going to look at the outcomes within the given condition. B, the person bought the song. So instead of my total number of outcomes being 5 people, we're only going to look at these 3 people. That also means the denominator of my probability equation is going to be the size of the event B, not the size of the sample space. So what is the probability of A, given that we're only looking at B? We're not looking at these. Well, okay, so the probability of A given B. So the probability of A, out of this B, there's only 2 people that attended the concert. 2 out of 3. 2 people out of the 3 people that bought the song attended the concert. So the probability of A given B is 2/3. So again, when we're looking at a conditional probability, the condition changes the denominator of our probability equation. The condition makes the total number of outcomes that we look at smaller. It changes our sample space. It reduces the number of things that could satisfy our event. Okay, this is not the same thing as A and B though. So the next thing they want to just double check that we're not confused. What is the probability of A and B? There's no condition here. So now instead of just looking at the highlighted part, I'm back to looking at the entire Venn diagram. So my total is once again 5. And A and B is A intersect B. So we're looking at these 2, the same 2 we were looking at in the conditional probability, but now it's out of all 5. 2 out of 5. Okay, so again, the difference between these 2 probabilities is the denominator. Because in a conditional probability, I was looking at a smaller set of outcomes. In a combined probability, we are still looking at all the outcomes in the sample space. All right, so here's our general equation for conditional probability. In order to find the probability of A given B, we look at the probability of their intersect, A and B, divided by the probability of the condition B. Okay, it's the exact same thing that we did up here, just in an equation form. To do that first conditional probability, we looked at the probability of the intersect, Bill and Zoe, was 2 out of the probability of the condition being satisfied. All 3 of these, 1, 2, 3, 2 out of 3. Okay, so this is our general equation that we can always use once again when we can't look at all the raw data and we want to just look at just the numbers. These equations are super helpful. And as you can see in the next example, we're going to be given just the numbers. So there is an 80% chance of rain tomorrow and a 60% chance of wind and rain. So that means probability of rain is 80% or 0.80. The probability of wind and rain or wind intersect rain is 60% or 0.60. So what is the probability of windy given that it is rainy? So make sure they wrote this correctly. Windy given that it is rainy. Perfect. Good. They wrote it in the right order. So based on what we wrote on the last page, that would be the probability of their intersect, windy and rainy, divided by the probability of the condition. That's the second one, rainy. And it's always going to be the second one. So the probability of windy, given that it is rainy, is, let's see, their intersect was 0.6. And the probability of it being rainy was 0.8. Okay, so we got 0.6 over 0.8. You can grab a calculator though there if you need to, or you can notice this is 3 over 4, or 0.75, which is a 75% chance. Let's try another one. There's a 30% probability that it will snow tomorrow. So the probability of snow is 30% or 0.30. There's a 15% probability that it will snow and classes will be canceled. So the probability of snow and canceled classes is 15% or 0.15. What is the probability that classes will be canceled given that it snows? So let's make sure they wrote this correctly. The condition should be second. The probability that classes will be canceled given that it snows. Good. So on the top, we have our intersection, classes canceled, and it snowed. And in the denominator, we have the probability of the condition, snowing. There we go. So let's plug in our numbers. The intersect, snow and cancel, was 0.15. The condition, snow, was 0.3. 0.5 over 0.3, that's 0.5, 50%. So a 50% chance of classes being canceled given that it snows tomorrow. So that means if it snows tomorrow, there will be a 50% chance of classes canceled. All right. Okay, so here's another application of that equation we had. It says if A and B are independent events, then the probability of A and B still equals this equation. This is the equation we've been working with this whole entire time. Okay. In the last section, we said that the probability of A and B, if we have independent events, this doesn't work for dependent events. If we have independent events, then the probability of A intersect B is the probability of A times the probability of B. So if I substitute that in here, probability of A and B is equal to the probability of A times the probability of B, you can see that we have the same thing in the numerator as we do in the denominator. So those cancel out, and we're left with just the probability of A. So that's weird. So what we're saying here is the probability of A, given that B has occurred, is equal to the probability of A if we have independent events. That actually should make sense. If two events are independent, that means that the probability of one event occurring does not affect the other. So if I want the probability of A, given that B has occurred, B has no effect on the probability of A. So the probability of A is completely unchanged. Okay, let's go back to some examples that we had of things that were independent. Let's see. We talked about rolling a die a whole bunch. Let's think of something that is not so trivial though. The probability of living in Alaska, given that you are 16 years old. Okay, those two events have no effect on each other. You're not more or less likely to live in Alaska, given that you're a certain age, right? So what is the probability of living in Alaska, given that you're 16 years old? Well, it would just be equal to the probability that you live in Alaska for any individual of any age, because age has no effect on where you live. Okay, so that's why that is. So that also means we can use this to test and see if events are independent. If the probability of A and B are independent events, and the probability of A is 0.85, and the probability of B is 0.4, what is the probability of A given B? So we would say the probability of A given B is equal to the probability of their intersect over the probability of the condition. But since these are independent events, the condition has no effect on the probability. So the probability of A given B in a independent event setting is just equal to the probability of A. So the probability of A given B is just equal to 0.85. There's no change because B has no effect on A. All right, let's answer some questions here. If the probability of A given B is equal to the probability of A, that would mean that B has no effect on A. So A and B are independent events. So there's a 30% chance that a randomly selected customer buys a salad for lunch. So the probability of salad is 30% or 0.30. There's a 30% probability that a randomly selected customer buys a salad given that they bought a drink. So the probability of salad given drink is equal to 0.30, 30%. What can you conclude about buying a salad and buying a drink? Well, the probability of buying a salad is the same even if the customer buys a drink. They're both 30%. So the fact that the customer bought a drink had no effect on the probability of them buying a salad. So buying a salad and buying a drink are independent events. And it says to explain. So I'll write P A given B is equal to P A. All right, so for this next part here, we're going to go back to the formula that we had on the last page. For dependent events, the probability of A given B was equal to the probability of A and B divided by the probability of the condition, B. So now we know we like these formulas. We can use these formulas to calculate probabilities with limited other numbers, basically. So we can actually use this in the next section. Let's go ahead and use this equation to get a new equation for the probability of A and B by itself. So I'm going to manipulate this equation so that A and B is by itself. So I have to multiply both sides by this P of B so that cancels, right? Whatever you do to one side, you do the other. So now I have that the probability of B times the probability of A given B is equal to the probability of the intersect, A and B. Or if I rewrite this a little cleaner, probability of A and B is equal to the probability of B, oops, where's my B? There it is, times the probability of A given B. Okay, so that's our next formula. The probability of the intersect A and B is equal to the conditional probability A given B times the probability of B, the condition. Okay, we could also say that it would be equal to the probability of B given A times the condition, in this case would be A. So there's our new set of formulas. To find the intersect, we had some formulas from the last section. Those are still good. But depending on the information that you're given, you might have to use this formula. Okay? So there's a 30% probability now that Malia makes her first free throw if she makes, there we go. Where's the rest of the problem? There's a 30% probability that Malia makes her first free throw. If she makes her first free throw, there's a 50% probability that she will make her second free throw. What is the probability that she makes both free throws? So let's look at what we got. The 30%, what is that? That is the probability that she makes the first free throw. And we have this 50% here. What is that? Okay, that's the probability that she makes the second free throw. given that she made the first 3 throw. Okay, and we want to find what is the probability that she makes both free throws, first and second. Okay, since all we're given is this information here, we're going to have to use one of these formulas. Okay, again, from the last section, we have some other formulas we can use to find the intersection. But since all we're given is one probability and a conditional probability, we're going to have to use one of these. So the formula that you use depends completely on the information you're given. So let's see. What's going to equal the conditional probability that I have, which happens to be second given first. And then I have to multiply this times the probability of this condition, the first. And luckily, that's the one that we have. So let's plug those in. The conditional probability was 0.5. And the probability of that condition is 0.3. So 0.5 times 0.3 is 0.15. Oops. So the probability that she makes both free throws is 15%. And I guess, yep, that's it. So I will hopefully see you guys in class week after next. Gosh, what is week after next? Where are we? 2/16. Ooh, next time I see you guys will be the last week before spring break. So that means next time I see you is the last week of third quarter. So make sure that you don't fall behind. Make sure you get this stuff done. If you get this last section done, this last quiz done by today, Friday the 19th, then I'll give you a little bit extra credit for being awesome. And hopefully I see you all on March 1st. Wow.